So yeah, this is the lunch and learn for the dynamic export component of Alice Springs Future Grid Sub-Project 5. Dynamic export, which was focused on the use of ComAp controllers. So thanks very much for coming along. So the idea for this trial came when I was working in the connections team at Power Services around 2019. So the Northern Territory government was launching their $5 million solar schools initiative that sought to add solar to a whole bunch of public schools. And around the same time, South Australia had started doing their flexible exports program, which is a residential program that looked at allowing people to double the amount of solar export that they could access if it was paired with the ability to turn it down to 1.5 kilowatts at times of requirement. So in the Northern Territory, solar sites greater than 7 kVA have historically been zero export by default. There was a process by which you could apply for export, but we won't have to sort of delve into that. In general, any site that was larger than 7 kVA has been zero export. And what that means is, unlike residential systems, they can only produce power to match the level of on-site demand. So that's what we're seeing in the graphs to the side here. The yellow is the solar, and if the solar would be producing more output than what is being consumed locally, its output gets reduced down to match that level. So it's not a case of the solar being exported and not being remunerated. It doesn't get created at above the level of local demand. Because sites have unique demand profiles, this zero export requirement impacts them differently. So a few examples: a sports stadium might have really small demand during the day, but huge demand in the evening when the big lights come on and the game starts. A swimming pool could be the opposite and have most of their demand during the day when they're pumping and at their busiest. In terms of schools, they've got low demand on weekends, school holidays and public holidays, or really any time there aren't students around, and that ends up being about 40% of the time. So observing $5 million being invested in solar for schools that would be heavily turned down nearly half the time was a problem begging to be solved, and really relevant for the Northern Territory government's 50% renewable energy target, which the Alice Springs Future Grid project was created to address. So that begged the question, what would be required to attain export allowance for larger PV systems? A couple of the requirements or factors as to why zero export restrictions have historically applied are LV visibility, so low voltage visibility, the ability to look at the part of the network where the embedded generation exists and understand what would the impacts be of that export on neighbouring assets or other people's systems or other people's houses. And then also the permanence. So all of the connection agreement terms are for the life of the system. If we grant somebody the right to export when they connect a system today, we're locking in any associated consequences with that export for 10 or 15 years of the life of the system. So even if you could do a good analysis on the consequences or impacts of PV export at the time of its connection, without a crystal ball, you can't look at what the impacts are going to be 5 or 10 years down the road. Some of the concerns are voltages, asset ratings, hosting capacity, impacts to regulating reserve, reduction in feeder and total system demand. And all of these things can be categorized as either a network or a system constraint. So looking at that, you could state that larger solar PV systems could be awarded temporary permission to export if either monitoring or modelling would show no impacts of concern for a given interval, and if in situations where network or system constraints were at risk of being breached, or if you could see that they would be breached, the solar can reduce its export to zero, and if necessary, its total generation. And this sort of a system is going to be more beneficial and more of a sustainable approach than making systems zero export. So that's largely what we're talking about. We're talking about the ability to dial in and tell a system for the next 15 minutes or for the next 30 minutes, we've looked into the situation and we think you can export this much, and that's not going to violate any constraint that we're looking at on monitoring. How can that be more beneficial? Well, solar export has the potential to benefit the system by virtue of an active power injection often being really useful. For example, when the frequency or voltage is falling during peak demand, or if power system assets are under strain. So if we're at midday on the hottest day of the year, the thermal generators are trying to deliver power while they're very hot, and they might really appreciate if we could tell the solar to increase its output and reduce some of their loading. Curtailed solar could be dispatched to mitigate dips in output from other PV systems. So a cloud comes over on one side of town, and all of the constrained solar on the other side of town could be told, you can increase your output, and we would attempt to regulate the PV as a whole using constrained solar to fill in the gaps. Of course, solar inverters can also provide bars to assist with voltage regulation. So there's definitely locations and occasions where solar can have negative effects. These requirements weren't created for nothing, but most of the time solar export is benign to the system and network, and if controlled intelligently, it can be quite beneficial. The minimum system demand thing has become really the dominant issue for industry, so I have to have a slide on that. For a really quick explanation, thermal generators require a minimal amount of load to operate stably. If you keep adding more uncontrollable solar and this drives down the load, the controllers are forced to run fewer synchronous machines because there isn't enough load to keep the required number online. And that then robs the system of essential system services like the capacity to regulate voltage, frequency, and ride through faults. So we can't allow demand in the system to continue to fall, at the very least until we've secured these essential services from other sources. And in 2022, Alice Springs actually operated below its security threshold for 19.5 hours, which works out to about 0.2% of the time. That's just a little look at what that looked like when we got to the lowest point in recent history. Quite a small amount of load for the minimum number of machines to sort of share to try to stay online. And that's when we're looking at a system that's at 13% renewable energy. When we try to model what 50% renewable energy looks like, you're talking about adding quite a substantial amount of solar PV. And it should be very clear that we end up approaching and passing zero if we don't have a way to control it. There is a view that you could just keep installing batteries endlessly to resolve the issue. I can go into it if people want to at the end about why that's not really feasible or necessary. But for the moment, let's just assume everybody understands that the control of solar is necessary and the right approach. So we communicated these requirements to ComAp Control, who I'd worked before with when I was in the solar industry on doing remote sites and standalone power systems and microgrids. We wanted remote set point control of inverters at a reasonably low price point. The sites should be able to default to a conservative operating state if they would lose comms. So if we wouldn't be able to communicate with them, we'd want them to automatically go to a conservative operating position. And anytime they would transition between set points, this should happen at an adjustable ramp rate. We don't want the situation where things are going to just step change quickly if we're talking about a large aggregated solar population. And it should also be possible to adjust any set points and parameters via API or via the internet, so the whole process can be automated, and it would otherwise not be scalable. We've always got to be conscious of if something requires human operation, then that's going to influence how large and complex it can become. Our price target was to get the system fully installed for sub $5,000, and we achieved the target. And at that sort of price point, you could reasonably require this control solution for systems as small as 30 kVA and still see it pay for itself within a few years under quite conservative solar export assumptions at the current feed-in tariff. It would cost recover much sooner than that if getting the right to export meant that you could install a larger system, or if the control solution would meet other requirements like revenue metering for large generation certificates, solar analytics, monitoring, the ability to do maintenance on the system, check how healthy it's going, and so on and so forth. This system also, performs the export control function that would normally be required of a zero export solution. So for that investment, you're actually managing a whole swathe of things that would normally have a cost associated with them anyway, which is really good. So we needed a site to sort of deploy this on. We worked with DIPL and Power Services on a connection agreement for Centralian Senior College, and we actually got them the right to export 100 kilowatts based on the control solution we developed, being able to manage the risks that were identified in that assessment. Our friends at Jakarta then agreed to pay the school the standard feed-in tariff, and a 60 kVA solar system was installed. We then basically increased the amount of export the site could do on weekends in stages, and had a look at the metering data to try to find any impacts to any of the customers in the surrounding areas, and couldn't identify any impacts whatsoever, even when the site was able to export at its full potential. Now, this system is unfortunately too small to really push the limits, and it can only ever export a small part of its allowance, and only on weekends. We have advised the stakeholders that with 100 kilowatts of export, they could easily install a system significantly larger, but I think that the issue is that the schools kind of roughly all receive the same amount of funding. So if we wanted to, go after this in a really aggressive way, we would have probably needed to have part funded that endeavour, which we didn't do. Having a look at a couple of the results, we often hear about solar being associated with voltage problems. So this is 3 days of unimpeded solar production down the bottom in blue, and then the impacts of the voltages at the top. For this site, we had to tap the transformer to its lowest setting, because it was sitting at about 256 volts average when we did the assessment, and that was actually an issue with getting the site connected. But now we've got it operating, you can basically see the voltage is actually a little bit lower while the solar's on than it is at night, and that's due to the effects of volt VAR, which the inverters just manage natively in this case. This is a similar test where I'm just turning the solar on and off every half hour, and again the voltage just continues on undisturbed. And if you wanted to understand why, you can see in the light blue line the inverters absorbing VARs to try to manage voltage as the system exports. It's just hugely useful to have this kind of data and be able to see how these systems operate, so we don't have to deal with these things in the purely theoretical. I might just quickly show you what the Centralian controller looks like, if that's still visible. It's just loaded for me. Can I get a nod? Yep. So this is the Centralian dashboard. We can see what the inverters are doing here individually. It's 230 kVA inverters. We can see what they're doing individually on the left-hand side. The first two dials we have here is the solar PV output and its set point. The N here signifies that it's an analog value, which is important. It means it's telling us that we are reading this from the inverter itself. So we can't get into a situation where we've issued a control and we don't know if it was achieved, because we're getting that feedback from the inverter directly. In this case, the inverter is being told it can go to 100%. So that's the unconstrained output. We can see the bus voltage and frequency, both of which are healthy, and what the reactive power output is of the site, which again, in this case, this is just volt VAR. That's the site managing it by itself. But it does have that desired effect of, if it tries to export more, it can increase its reactive power contribution to make that manageable. So for this section of the site, they're currently using 9 kilowatts. The solar is meeting most of that local load, and then we end up with the Q value as well. So the controls, all of which, as I mentioned, are mapped to API. So this could all be done automatically using an internet-based system. We're able to basically just issue a set point in fine granular fashion. If I wanted to tell this site to stop producing solar, it's as simple as that, as changing a value. All of the controls are in percentage terms, because everything is in relation to the rating of the inverters. So if I tell the site that I want 500%. I'm effectively saying I want 300 kilowatts of load, which if it can't do, it's just going to ramp the solar down. We're able to see the ramp rate in effect, the set point trending down towards zero, then the solar following it. A couple of other things, we've got the fallback position. So this is saying that if the site loses comms, if it loses its connection to the outside world, in this case, we're asking it to go to zero export. If it loses its connection to its meter and no longer knows if it's exporting, we're asking it to go to a 25% power point. And then we've got here the ramp rate to specify how quickly any of this can happen, which is currently set at 150% per minute, so relatively fast. And as you can see, the solar is being dialed down. It's just reached zero now. It didn't do that in a single step. It did it at exactly the speed we were able to specify. And then we've got some PID tuning factors that impact some more of how the site will maintain its set point. I'll get the site exporting again because I always prefer solar export to happen. And we can have a look at this in more detail a bit later on if people want to ask any questions about it. We did another deployment of the controller at Temple Bar. This is a power and water services site, which is a water pumping operation in Alice Springs. And we wanted to basically take the next step, which we saw as making the set point sensitive to frequency. This means that we can have a set point that's suitable for normal conditions when everything is happening as planned, but that export set point can automatically adjust in contingency conditions. This requirement was largely inspired by reading the 2019 Alice Springs System Black report, which happened on a Sunday, I think at around 3 o'clock. And because it was a Sunday, we can assume that most of the commercial solar out there would have been in zero export mode, constraining its output. And when the frequency was falling and the system was in dire need of an active power injection, the solar would have dutifully ignored that rather than increasing its output. So that's really the idea here, that the system can see the frequency falling, know that the power system is demanding more active power to recover from something that's gone wrong. And why not get solar to contribute to that if it's able? The controller has both a regulation band for gentle adjustment and a contingency band for aggressive response. So whatever we set the site export limit to, it's going to raise and lower automatically with the frequency to support the system in a fashion adjustable by the controller. We also enacted something called closed loop voltage control, which means rather than the inverter absorbing VARs as required based on the voltage that it sees, we can actually set a voltage target, and the inverter will try to generate the VARs sufficient to achieve that set point rather than just reacting to the voltage as it happens. So this is a bit of a look at how the droop response works and what the controllers are able to set. They can determine the band of regulation, so where the frequency can go, where it will only trigger a gentle response. After that, you're in the contingency and the response is more aggressive. And of course, you can set the export where you want it. So in this case, the site's sitting at 50 hertz, exporting 100 kilowatts. If the frequency were to fall to 49 hertz, the site would suddenly be exporting 250 kilowatts or thereabouts. So it's going to increase its output to try to help the system recover the frequency. And of course, the opposite is true. If the frequency were to rise to the 51 hertz, the site has stopped exporting at all, and it's actually started forcing the site into a position of load. So we can take it further than zero export, which is again an example of why a zero export system is less powerful than this. We can reduce the generation, until the point that it's completely at zero, where that's required to support the system. That's looking at what this looks like and kind of how powerful it is. So in this case, 28% corresponds with a set point of 100 kilowatts of load. I did this over the weekend. We asked the system to be at 100 kilowatts of load. It limits the solar in orange to try to maintain that green line on exactly 100 kilowatts. In similar story with the voltage, we've got a set point of 240 volts, and there's the VARs adjusting as required to maintain that set point. And this is, operating the system in a heavily constrained fashion. but it's used here to illustrate that point that with really powerful controls, we can achieve a system that's much less variable than the site would have been without solar. But the voltage and the load can be what we set it at. So we're always associating renewables with increasing the variability of the power system, but with good controls, that doesn't have to be the case. And that capacity to constrain. And probably the last point to make on this controller before we jump and have a look at it is even when we operate it with no active power, when we set not only the export but the generation all the way to zero, the system's still able to provide that reactive power support to help regulate the voltage. So this is more powerful than just turning inverters off. We can use their ability in this way to benefit the power system and still create value, which is useful and can offset the need to invest in other solutions that can do that. So a little peek at Temple bar controller, which is a bit more complex. It's 6 times the size of the Centralian one. There's 6 inverters at the bottom, one of which has a problem that somebody can go and investigate. And again, this is the power of having that monitoring and being able to see huge amounts of data on each of the individual inverters and how they're performing. Water Services does know about inverter 5, and so does the solar installer. But we've got here, what the solar output and the set point is, what the inverters are doing in terms of their total capacity, where the voltage is sitting, which is exactly where we've asked it to be, and this this droop function telling us where we're sitting at in the band and how that's adjusting. So we've asked for about 100 kilowatts of export, and this is telling us that currently you're sitting bang on 50 hertz, and that's what you're getting. But if this were to change, so too does the export set point. In very, very, very minor terms, it's difficult to see because in general the frequency is very, very healthy. It's only when things go wrong that it's going to move the needle in a meaningful way. Over on the control side, it's the ability to set the export limit, which minus 28 corresponds with allowing the site to export 100 kilowatts. That's probably appropriate during the week, and on weekends we might go the other way. Again, fallback positions, the speed at which this thing can move between set points, what we want the voltage to be, and then what the settings are on the droop response. And all of these things can be turned on and off as required, as well as dialed in whatever we want the gain settings to be. So in future versions of the controller, one of the things that we probably seek would be to have different RAM rates for different parameters. For something like a droop response, you really want the set point to be achieved extremely quickly. And that's different to the case of if we were making a transition that should happen over minutes. So you probably want to go in and add that ability to specify ramp rates for different functions. We'd also want to be able to at least monitor power factor correction, grid protection relays. These are other components of the solar system or of the site that would be useful to at least monitor, if not control, and be able to observe how well these assets are performing in relation to each other, noting that they can get into hierarchical conflicts in how they operate. It would also be really powerful to be able to incorporate controllable loads and batteries and be able to see the control system use more things available to it to achieve the set points as we make them. And eventually you want to integrate Web Supervisor to Pi, which is our data repository at Power and Water, and that's going to be the thing that will allow the system to be operating fully autonomously. We have as of last week achieved that using a different trial involving redback inverters on public housing sites, which will probably end up being its own lunch and learn. But effectively, a system we're working with called GridCube is able to produce set points based on whatever constraints we feed it. In this case, we just ask for it to alternate between 5 and 2 and ignore anything else to do with the system. But in general, it would be looking at what's the temperature of this transformer, what's the loading on this conductor, is the power system within the limits that are being specified. It calculates an envelope of permitted operation in terms of how much export and import can happen. And over on the right, we're seeing that being realized on the sites. So no human has to touch a button. The the set points are generated based on the constraints that we feed it. And we use a solution called GreenSync, which interfaces with Pi to deliver those set points directly to inverters. The other thing you can see on the screen is dispatch status started. So the system is even clever enough to receive from the redback inverters. I've understood the instruction you've given me. I've actuated that request, and this is now in operation. This is the sort of thing that would allow you to do it on thousands of sites and not require a huge team of people sitting there being able to press the button and being able to do it at quite minute intervals. The last slide, just to sort of finish it up before we jump into any other Q&A or looking at the controllers in more detail, I just sort of wanted to note this, and we recently got the feedback from the virtual power plant we did in the Future Grid project. And one of the views that was there, as is always the case in any media report I've ever read, is this idea that controlling solar is a really bad thing. It's not something the public presently accepts, and even the media that's generally very pro-renewables sees it as a very negative thing to control solar systems. That's okay if that's sort of the prevailing view, but what that really tells us is we've got our work cut out for us to be able to explain to the public why the ability to control their solar is actually really good for renewables. This control is actually how we allow more solar to be installed, both on individual sites and future sites. It's how we allow those systems to be larger and to export more into the grid when it's safe or advantageous for it to do so. So really the risks and the concerns that we have about what solar does and how it affects the power system can be managed through intelligent control. And I think that's really key to how we can transition to 50% and beyond. It's the thing that kind of pairs with the technology is the participants being able to achieve those benefits so that this can become more widely accepted. And that's going to eventually lead to much more upside for the people that are getting it and the people that will get it in the future. So that's the presentation. Yeah, happy to hear any questions or dive into more detail on the controllers themselves if anybody wants to have a look.
Thanks, Thomas. Adam here at Power and Water. Did you say that the inverters can actually create load as well, or create kVAR?
They can create reactive power, or in this case, it's generally absorbing reactive power to achieve a voltage effect. And what you can kind of think about it doing is it sort of just sucks in power that's at unity or whatever it's in, and then puts it through either an inductive or a capacitive stage to shift the voltage and current waveforms, and that's going to have an impact on the voltage. So yeah, it performs the function of a voltage regulation service without needing any load or any power on the panels for that to work. Yeah. It's more basically a filter. Yeah.
Right. Might have to catch up with you after about our power factor correction and that, and work we're doing at Temple Bar just to make sure it's all.
Yeah, that's a bit of a passion point for me, and it was a disappointing thing in this project that I didn't get to monitor both power factor correction and volt var, because these are competing set points effectively. Yeah.
Hi, Jo Keeban here from DIPL. Can you hear me?
I can, yep.
Yeah, thanks. To build a business case for PV systems, you need to be able to predict the amount of time the output would be constrained by power and water. How can you foresee that rolling out, being able to predict that?
Yeah, it's a little bit difficult, particularly when we try to be sort of future focused. I did make this point in here for that reason, that the main reason we talk about controlling solar in 2023 is about falling minimum system load. We fell below the minimum system load threshold last year for just 19.5 hours. This is something that happens predominantly on weekends and public holidays in the really mild months of the year, where solar is booming, but in places like Alice Springs, you don't need to heat or cool your homes because conditions are pretty mild. So it's not all the time. And the general expectation is that you should be able to export quite well, but it would be difficult for us to kind of put a value on it. I think that the general advice can and should be, you should still be basing the solar system you attain on the load for your site. It should be really predominantly about how much you expect the site to need. And then export opportunity can basically be icing, which would be more applicable situations like on a weekend if your commercial site wasn't operating, and then it's just better to sell it for something than it is to turn it down, irregardless of whether or not there's an active risk or constraint applicable at that moment. But yeah, the business case should be on being able to use it. I think to use an example like the one we saw before of a sports stadium that's not really using any power in the middle of the day, they probably shouldn't invest in a huge system based on the hope of exporting unconstrained a lot of the time. It's very possible they will still be constrained due to voltage or overwhelming their applicable transformer some of the time, and it's not good to, I think, base the business decision on export. It's just good if we can allow it where possible.
And I assume that over time that the number of hours a year that sites were constrained will be available and we'll build up that knowledge base.
It's, yeah, and that's another really good point. It's the case today that if we could control new solar systems, we'd be turning them all the way to zero a lot of the time because there isn't enough controllable fleet to maintain the targets that we have. Once this would be most systems, they would all be sharing that burden, and that might mean you're only turning them down by 10 or 15%, and they barely even feel it. So it's a lot of it is about the equity of the controlled versus the uncontrolled population. And then also a specific investments are made as we would add syncons or batteries to Alice Springs, we would be able to lower that threshold from 8 megawatt to something lower and open up that hosting capacity for more export. It gets into a whole topic of what is the value of constrained solar and at what point should augmentation be made to facilitate more export. Thomas Wearne.
Thanks, Thomas. I wanted to check that I understood something correctly, that you suggested that the control mechanism that would kick in under contingencies, which would be different to normal operation. Is that a good? Is that a correct understanding? Yep. What are you suggesting would be a trigger for moving into that alternative operation mode?
Well, the trigger is the frequency that the site sees. So obviously any solar control or solar export control system is going to have a point of reference. It's going to have a meter. In this case, for Temple Bar, we've got a very high quality meter. And the advice from ComAp, who are on the line, is that we would probably be able to detect this as quickly as 500 milliseconds. We don't have, certainly in Web Supervisor or in our meter or anything else, the ability to confirm that. And this should really be tested with a high-speed logger in a controlled environment, like the testing we did at the CDU testing facility, which is for exactly this type of thing, where we can induce a contingency and observe the effect in millisecond resolution. But basically, the site detects the frequency, it adjusts the set point, the inverters will respond as soon as they're able. And in my understanding, solar and battery inverters aren't really all that different. It's just a question of how bulky is the DC supply of power that would govern that operation. But they can adjust their output very quickly. It's very easy for me to demonstrate by just making the ramp rate as fast as possible and changing a set point. And it basically is just a very, very, very quick response once the new set point is issued. So happy to hear more from Jeremy and ComAp about that if you're interested. But yeah, my understanding is, didn't want to call it FCAS, but certainly you'd be able to get a very quick response from a system like this. It's just difficult to kind of test without investing in the monitoring gear to do so.
Okay, so that group setting would be would be in place all the time, but it would only affect the operation if you had a significant change of frequency.
No, it goes all the time, unless we switch it off. So we can turn the drip off here, and we can set the thresholds at which it happens. When I showed this to controllers, it was great. They said, "Oh yeah, put it on 4%." That would be good. When we look at the trends, you can see it work, but it's obviously just sort of 1 minute averages, which is not really the right kind of level. But we end up with basically a constant, very, very small change in what the export limit is relative to how we've set it, based on a little bit of bias. That's loading for a full week, so that's going to be a bit annoying. Just doing it for today. So small changes in frequency result in small changes in the drip bias out, and we can also add in what the PV set point then becomes, which I'd normally look at to understand, yeah, how you're actually changing the system based on frequency.
No, thank you. It's quite clear.
Yeah. Cool. Terry?
Hey, Thomas, I don't know if you can hear me okay.
Yep.
Cool. First of all, excellent presentation, because it gives a hell of an insight into the facilities and tools that could be available for the integration of DER, or the demand side, and how to get the best out of it. This is a trial, and this is really, you've proven a concept here that probably hasn't really enjoyed the level of detail and insight that you guys have done in the Alice Springs Future Grid. What do you see as the next steps in terms of looking at how this could ultimately become a mainstream capability that is offered by licensed network providers, but also system operators, to be able to harness value from the demand side end within power systems?
Yeah, I mean, the potential is staggering. We had that kind of price point in mind because we wanted it to work that way. And, it's not to say that we got it to 5,000 a unit instantly. These capabilities didn't exist, so we had to fund them through R&D developments with ComAp. But once they were created, they're effectively just lines of code that can be redeployed on sites as we like. And it then kind of just gives you this sort of menu that a customer would connect, and we could set the type of voltage control we want. If you wanted the droop control, et cetera, et cetera. It's all basically then just adjustable, and because it is lines of code, it doesn't change the per unit cost once you've developed a particular capability. So you could, I think, reasonably require this of all new solar sites of a particular size. For the small investment needed to get the control, customers would be accepting that they're going to have their output turned down some of the time. That would be using the system control license, so we have to have a good justification for when we use it. It's not just a trigger-happy tool. But then on the upside, instead of setting the amount of export they're allowed based on the really conservative look ahead of what we think is going to happen in the next 10 years, we only need to allow export for the next 15 minutes or the next 30 minutes based on that GridCube system that's evaluating all of the constraints in near real time. So that's the vision, that we would basically have a system capable of analysing any constraint that we ask it to. We'd be able to feed into that parameters as required, and the set points would get generated and delivered to sites automatically, and wouldn't require, I think, human operation. So it doesn't have to be, I think, terribly expensive, but it can be hugely powerful without changing too much what the experience is for the customer, or what the investment is in the solar to begin with.
Yeah,
the biggest, most challenging thing is convincing people that this is justified and beneficial, because as I say, the view of the people right now is, don't touch my solar.
Yeah, and in particular in Alice Springs, where you sort of hitting those system constraints, especially at network minimum conditions, this potentially provides, and if it is relatively affordable, especially down to the granular residential type environment, you could probably be able to better manage PV-rich feeders under minimum demand conditions and offset significant or substantial further investment required on the supply side.
Yeah, and that's exactly one of our tests that we've got GridCube working on. So this is looking at Pi Vision. I gave GridCube 2 levels and said, I want you to keep this feeder load between, I think I said 2 megawatt and 0.8 megawatt, just arbitrary values. And from that, they go and generate individualized set points for all of the NIMIs that are downstream of that feeder. We've only got a small number of sites in this trial, but it's then able to, be basically achieving the loads as you require them, and making these sort of small adjustments in how much export people can get based on what the loads are at the time. And we're going to go from doing that at the feeder level to doing the whole of the system level probably this week. But I think that anytime you can think of why we would have a good reason to need to constrain, that's something that can be automated. It's something that could just be converted into a code-based approach where we either pull the relevant parameter out of the system or enter it as a field in Pi for controllers in real time that are running the thing. Gordon?
Hey, Thomas. That's really awesome because a lot of these solutions are pretty DNSP focused, and obviously you're taking in system demand and frequency concerns into consideration as well with the solution. So market operator gets a little bit of a tick there too. I guess the one question I have is with those constraints, because sometimes obviously the voltage and the demand requirements can be conflicting if you're looking at it from the load side of things. When you're looking at the voltage side of things, and you have the demand side constraints, which one takes precedence?
Yeah, that's a great question, and I think some of the time we're affected by what the inverter will naturally do. So to give a good example of that, just jumping onto the Ben Hammond site, if I ask this site to give me 100% in active power, and then I go ahead and ask it to give me 100% in reactive power, the inverter is Q priority, and it will choose Q over P. So some of the time you're dealing with how the system does that natively, and other times you're going to need to build it into the code. So it's a good point. We could probably specify the droop curve that I showed previously should only operate when we're sitting between 220 and 245 or something like that. Some value where we're not going to get into the situation of injecting power, raising the voltage, and causing other PV units to trip, for example. So you've just got to develop all of that logic and build it into how it operates. But we've seen a lot of examples of conflicting control requirements where systems compete. And this is something not just relevant for us in the NT, it's really a whole of industry issue of how different things should be prioritized when they're in conflict. So fully agree, it requires a bigger deep dive for us to set the standard of how and when things should respond based on other related conditions.
Perfect.
So that's going too slow for me to make my point, so I'll speed it up. Yep. Well, so yeah, the active power goes down in this case to 0, and the inverter's going to operate in full Q. And the cool thing about this is, again, that it's not limited by what's happening on the DC side in order to do that. But it looks like it might be choosing to embarrass me, or at least it's holding on there. But you can see that it is working. Looks like we might have run out of questions, which is probably good. No difficult, hairy ones for me?
Joe, Kim, and I don't think this is difficult or hairy, but I thought it was not technical enough, really. But so the ComAp is a device that you attach to the inverters, is that right?
Yes.
Right.
It is.
And how many inverters are compatible with it?
Most of them, certainly. So in this case, you're talking about local, they call it Modbus TCP control, using an open protocol called SunSpec, which most inverters speak. We didn't find any example of an inverter that we couldn't control with the ComAp solution, but there are some exceptions, and one of those exceptions is Redback, which we talked about previously. So you do get the odd inverter that doesn't want to be controlled locally by somebody else's hardware, in which case the version of control is this API or internet-based approach, which you can also do. So it's either a local hardware controller or you're relying on what the API is able to do, and you really want to design a system that can do both. So ComAp aren't the only control system solution out there. We've also worked with one of their competitors, Azo Automation, to produce a second controller, not wanting to give any individual company a full monopoly. And we've demonstrated here a version of it with no controller. In the virtual power plant, we worked with Switched In that also do both local hardware control and API-based control. It ultimately depends on what you're trying to do. And I think that, yeah, for the 30 kilowatt and above type system, requiring a hardware controller or requiring performance functions that are only achievable with a hardware controller is fair, because, as I said, that sort of $5,000 cost isn't going to make a system unviable. And then when you're looking at the residential scale, probably you want to avoid any requirements that are going to involve hardware, because it's going to add at least $1,000 or $2,000 to the site and discourage participation. So it's looking to me like API-based control for residential and hardware control for small commercial and above is probably the sweet spot in terms of how you would distribute performance requirements on DDR.
So it's not technically impossible to retrofit this?
No, you can definitely retrofit hardware controllers for sure, and I think that it's always going to be a little bit of a case of, you know, the Lion and the Gazelle both getting faster. Inverters are going to keep getting more clever by themselves, and control companies like ComAp are going to keep evolving to have more sophisticated functions as we think of things for them to do.
Also, the Temple Bar was a retrofit too. So.
Oh yeah, Temple Bar's a retrofit for sure. So the ComAp solution actually replaced a much more complicated and much more expensive solution involving cloud cameras and attempts to ramp the output in a controllable way, and ultimately a lot less powerful than this and a lot more expensive. So yeah. Okay.
I think he just left.
So Thomas, just jumping on that, there's viability. So from an industrial type application, it's not a hurdle that is insurmountable in terms of cost, and you could easily look at what the actual cost is of providing supply side solutions to have uncontrollable capability versus putting some controllability in like this. And then when you get to the residential level, well, what I was seeing is that you don't necessarily need any hardware, and the actual cost to participate is actually pretty low. So in answering that question earlier from DIPL, is you could very easily retrospectively apply the residential type environment with a limited cost. So your exposure to cost is not substantial, and it did speak volumes in terms of competing against having to invest in much larger supply side solutions. Is that correct?
Yeah, I mean, we need to change the way we connect customers. That doesn't happen overnight. It involves having a conversation with them, with the installers, with the community and everybody to understand it. And then we need to be ready to have systems on our side that can actually create the set points and not have undesirable effects. So I think it's all iterating in a really healthy way. Should shout out to the Power Services Power Partnerships Initiative, which effectively is about getting larger customers to agree to let us turn them down at these key moments. And this control solution is probably the most feasible way to do that under bespoke arrangements with particular people. So I think the conversation that hasn't necessarily happened yet would be to start with the NTG and say, where else do you have solar sites that we could add this controller to both enable export, which is good for the renewable energy target, and be able to turn it down, which is good for hosting capacity and keeping the system secure. So that's the conversation that does need to happen and is happening. And we would, from there, be able to eventually, once we're able to, probably just make this a mainstream requirement, which is, we wouldn't be the only place in the country to do that. It's like Jordan wanted another turn, and then not Jake, but somebody with Jake's name.
Mario. Jake's team can go first. I'll go next.
Okay.
All right, it's me, Mario Thomas. We are using Jake's account.
I love that you said that. Yeah, go on.
I have a question here. In regard with the AS4777 F inverter had this frequency and voltage protection inside, right? And then with the ComAp itself, it has its own frequency response. Will it override the ComAp controller when something like trigger the frequency on the inverter, or how it's going to?
Yeah, no, that's a hugely good point. No, we haven't disabled the protection settings in inverters. So while my graph here might show things happening at 54 Hertz, the inverter disconnected way before that. And it's fine that happened. The curve is sort of there to illustrate a point, and hopefully the frequency doesn't change by as much as it would have otherwise if you hadn't provided the response. But it's still the case that the behavior you've come to expect will happen. The inverter will disconnect at the points specified in terms of voltage and frequency. We haven't changed that. Maybe there's some argument that we could or should, but we're not looking to deviate nationally from how inverters respond natively. We're just working within the bands before they trip.
Okay. Thanks, Thomas.
Sure.
Perfect. And I guess I got one little hairy one for you, Thomas. If say we were to build a utility server or 2030.5 server or a CCIP Oz equivalent, would that be able to would that easily be able to integrate with these solutions, or would it be an entire revisit of the whole thing?
I think that would basically just require for ComAp to develop their CCIP client, which I'm sure they'll do if that does become the dominant protocol used by industry. So it wouldn't be an API-based control that would require a specific integration between 2 points. It would just be a language we all agree to speak. And ComAp, like a lot of other control providers, would be able to offer that as a service to inverters to interpret and operate using that protocol, and us if that was what we were able to do. I don't think that it always has to be either or. CCIP Oz can be one of multiple control options that you can deploy, but I would fully expect that that to be where industry lands based on current predictions. And I guess the other possibility is Web Supervisor could be developed to have aggregation capabilities, and that would push forward in time when integration is really necessary. If we were able to grab all of the Alice Springs inverters and there were 500 of them and give them common set points, then we wouldn't need to be able to manage the system autonomously quite as quickly. So I think both things can happen, and it's just a question of moving with industry and recognizing that we're a small region and we don't get to set those trends.
I just Adam here from Water Services. So we're the owner of the Temple Bar pump station, do all the pumping, and just from our experience too, just like to say thanks, Thomas, and really support it as like an industry user, as power consumer / generator. yeah, it's got big benefits to us where we've gone from zero export now to being allowed to export, so there's a little bit of, we'll yet to see if it will actually be any revenue, but
you probably need to get in touch with Jacana and ask for a feed-in tariff.
Yeah, so, but it, it has simplified our system, like that the cloud camera stuff, it created grief for us and things, so just from a industry experience and on the other side of the fence to Thomas, although I'm power and water, I'm still more like, a power consumer. It has been, a really productive system and ironed out a lot of the issues we've had out there, and I think there's a lot of opportunity with this stuff. So thank you, Thomas.
Thanks, Adam. And the red line here is your load, and just for anyone's interest, that's what a step change looks like. That's when a pump goes off, and that's when a pump goes on. They're big steps, and if this system could be trained to pay attention to that variable and try to respond to it when it correlates with the solar or if battery storage were added. So there's definitely lots of ways to skin a cat, and I think that there's specific risks that meant that you needed to have that ramping solution back in the day. Could be continuously improved upon with this controller. But no, great to hear that you've see benefit in that outcome. Have I given you a login for this one, Adam?
No, not yet. I wouldn't mind catching up with you a bit more after.
Yeah, sure.
Yeah, please.
I've given it to a number of your colleagues, but that's fine. We'll get you logged in.
Yeah.
All right. It's got to be time.
Sorry, I'm a bit vocal. Joe Keevan from DIPL. Just one other point I wanted to make, that we're really keen on thermal storage in mechanical chilled water systems and the capability to use that as a mechanical battery, really, and look at when chillers are running and not running. And that adds to the whole distributed energy resources picture for the territory, particularly as we've got cooling loads all year.
I don't think that there's anything that ComAp can't control. Not to do the sales pitch for them, but solar inverters are what we contacted them to muck around with. But anything that's got parameters and digital signatures can be operated, and I'm sure working with thermal storage would be another really exciting case study and application. So if there's a site that wants to do that and the thing has a controller, really happy to explore it. I think that would be huge potential.
Well, Charles Darwin University, Casuarina campus, good place to start.
Yeah, let's do it. Thumbs up.
Oh, yeah. All right. And thanks, Thomas, for running this session. I think there's been a lot of questions, and so thank you for this, and it's really good. Future Grid, of course, though, is wrapping up soon next month, and so I think it's really good to have these conversations about what could come next, what's required. And thanks too for everyone's question, Adam, your experience. It's really good to hear. Sometimes that other side of being involved, that customer side, and thanks.
Beautiful. All right. Thanks. I'm going to give you a wave. Thanks. And please get in touch if there's any more questions or anything else you want to understand or dive into.
Thanks, Thomas.
Thanks, Thomas. That was excellent.